We've all known for at least a few decades that Earth undergoes something called plate tectonics. But what if I told you that tectonics doesn't always involve plates? That is, plate tectonics is not the only way that a planet or moon can undergo tectonic activity. And even our own planet Earth has undergone different tectonic regimes throughout its history. It hasn't always undergone plate tectonics. So that is what we'll be talking about in today's video. The evolution of tectonics on Earth, the timeline of it, what kinds of tectonic regimes we think were going on early Earth, and all of that. Before I jump right into the video, this video is a little different than my normal sit down and talk at you videos. It is me sitting down and talking at you, but I have a special guest. Because this is not my area of expertise, I invited on a fellow YouTube creator and science communicator, Stephen Baumann, to talk about some of the processes we think have gone on tectonically throughout Earth's history, especially on early Earth, especially throughout the Archean 2.5 plus billion years ago. And he has so much more material that goes so much more in depth on his channel. So at the end of the video, I'll kind of shout out some of the videos you can go check out on his channel that will take you even deeper. But thank you so much, Steve, for coming on and talking about this stuff. You are just so brilliant within this realm. So thank you, and we'll get started. Before we jump right into tectonics and tectonic regimes on Earth, let me just kind of briefly introduce the basics regarding tectonic plates currently on Earth and kind of some definitions regarding the layers of Earth so that you understand the terminology as we go through the rest of the video. So first things first, I do actually have a video called something like tectonic plates versus crust or vice versa. These are not the same thing. As we can see on this picture, it is not that the green parts, the continental land masses, move about the blue parts, the ocean. The oceans are part of the plates. Continental and oceanic crust make up the tectonic plates that we have on Earth today. Why? Well, it has to do with kind of the definitions of layers on Earth. As I discussed in that video, the lithosphere is what makes up Earth's tectonic plates, and the lithosphere does not equal the crust. It contains the crust, but it also contains the uppermost part of the mantle. Essentially, there are two ways that you can define layers of Earth, and here's how Steve puts it to clarify things.
There's two different type of layers, generally, if you will, of the Earth. We have compositional and mechanical. Mechanical layers are what tectonics and structural geology we all deal with. The compositional layers, there's three. You basically have the crust, the mantle, and the core. And then you have two types of crust, continental and oceanic, or felsic and mafic. But mechanical layers, you have the lithosphere. Now, the lithosphere, for anyone who doesn't know, is the upper part of the mantle. And on top of that sits the crust. And the crust is also part of the lithosphere. It's one of those annoying definitions where you kind of got to differentiate if you're talking about like just the mantle part or the crust part. But these are the plates. The lithosphere behaves the same. You know, the lithosphere gets subducted with the crust. It's not just the crust going back in the mantle. It's that upper mantle as well, the lithosphere. So it's a little thicker than just the crust. So mechanically, when I talk about plate tectonics, I'm talking about mechanical layers. I'm not really talking about compositional.
So this is why some lithospheric plates contain both continental and oceanic crust. It's because the lithosphere is really that uppermost part of the mantle and whatever crust lies on top of that, not just the crust. Therefore, it's broken up differently than the boundaries of continent to ocean. So now that we know the lithosphere is the layer of Earth we're talking about when it comes to plate tectonics, what exactly is plate tectonics? Well, first let's define tectonics.
The definition of tectonics, I just have the deformation of a planet's lithosphere caused by a planet losing its internal heat. And that drives every terrestrial planet's tectonic system. It's just, how does that body get rid of its internal heat? That's really all it is.
But what makes tectonics plate tectonics? When do we call it plate tectonics? Well, Steve says it's as simple as it must involve plates. So what are tectonic plates? How do we define these? Well, Steve says,
And then we have the definition of a plate: physically separated segments of the lithosphere with well-defined physical boundaries. For example, spreading ridges, subducting trenches, and transform contacts. Spreading centers, convergent margins, that kind of stuff. A lot of people think subduction equals evidence of subduction equals evidence of plate tectonics or evidence of crustal recycling, thus for plate tectonics, and that couldn't be further from the truth. To have plate tectonics, you have to have plates. You don't have plates, you don't have plate tectonics.
so essentially, as Steve mentioned, tectonic plates have to have well-defined boundaries. Boundaries where they're pushing together, causing what we call convergence zones on Earth, where, if it's an ocean-continent convergence zone, the oceanic plate or the lithospheric plate containing oceanic crust subducts underneath the one containing continental crust, just because the continental crust containing lithospheric plate is more buoyant. We'll get to why that is later on. And this creates what are called subduction zones. As he importantly mentioned, subduction zones are not evidence for plate tectonics because we do have regimes in Earth's really early history that may point to subduction without the need for plate tectonics, and I'll get to that later as well. And then also some other well-defined plate boundaries are things like mid-ocean ridges, where plates are pulling apart, causing new ocean crust to form, or continental rift zones, where the same thing is happening, but in a continental crust containing lithospheric plate. And also the third type, or the third major type of plate boundary is transform plate boundaries, where plates slide against each other. So push together, pull apart, and slide against each other are the three kinds of plate boundaries that define tectonic plates on Earth. So we have tectonics, which is how a planet, in this case Earth, loses its internal heat. And we know that plates are required for plate tectonics. And we talked about how plates are physical segments of the lithosphere with well-defined boundaries. So do we have a good definition of plate tectonics overall? Well, here's what Steve says.
Plate tectonics is a tectonic theory that explains the formation of geologic features caused by how a planet loses its internal heat. And the reason why I have tectonic theory is because a lot of people think plate tectonics is just continental drift, and it's not. Continental drift just says the continents move about the globe. That's really all it says. But a lot of people think the continents sit on the ocean floor and slide around.
Yeah. Mm-hmm.
And that's not it. Continents are part of these plates. The planet is divided into rigid plates with well delineated boundaries.
He also goes on to point out the lateral nature, or kind of horizontal or side-to-side nature of plate tectonics compared to other tectonic regimes. But we'll talk more about this later and how other tectonic regimes in Earth's history have been more vertical compared to lateral, like plate tectonics, and how these different tectonic regimes and their more vertical nature affected the geological features forming at that time. But Steve also made sure to stop before we moved on to discuss what drives plate tectonics, because we can't have a good theory without talking about and understanding the mechanisms behind it. So what does drive plate tectonics?
These are the three dominant mechanisms that we suspect happen. Slab pull, which is at convergent boundary subduction zones. Mantle convection happens in the interior of the Earth, and that's the one that everyone's familiar with. That's the one you see in National Geographic and all that stuff of this churning mantle like it's liquid. The mantle's a solid. Most people don't realize that. Yeah. It's just any solid will experience three general deformational experiences. Elastic, which means it pops back to where it was. You ever lift something heavy and it hurts your arms, that's because you're in that elastic limit and you better stop what you're doing. Plastic, which is a permanent state of deformation. Once it's in that stage, it can't go back, only elastic. But eventually, you ultimately get to brittle failure, and it just snaps. And that's what gives faults. The reason why we don't get earthquakes deep into the mantle is because the mantle is plastic. It's in that state of plasticity, constant. And its plastic regime, if you will, is very large compared to any sort of brittle or elastic deformation. we used to think that was the driving force. And even my tectonics book kind of says that. Well,
Mhm.
out in the 1970s, there was a couple of papers that came out about slab pull. And we knew subduction happened then. We just didn't think this was a thing really affecting plate tectonics. Well, first of all, we can discount ridge push. Ridge push is not powerful enough. Those
Okay.
are shallow magmas. You can melt rock not only by heating it, but also adding water and releasing pressure. That lowers that melting curve. And that's essentially what's going on at the mid ocean ridges. So that's not powerful enough by any means to get this
Okay.
system going. We know that. We've always known that. So it's between mantle convection and slab pull, we think. Slab pull, like I said, is a concept from the 70s that as these ocean plates get old and less buoyant and thicker, that eventually they experience brittle failure, you get faulting, and then gravity takes over, gravity driven system. And
Mhm.
that starts to subduct it. Well, and since the plates are rigid, something's got to happen somewhere else. You can't just, so it's going to experience brittle deformation somewhere else. We think it's slab pull is the number one, mantle convection is number two, and ridge push is kind of just like a side effect of this gravity driven system.
So now we know what plate tectonics is, what the plates are made of, how they move, and what drives their movement. But plate tectonics is only one tectonic regime. As we talked about at the beginning of the video, it turns out that Earth has not always undergone plate tectonics. So when did plate tectonics begin on Earth, and how do we know that it was not operating on early Earth?
2.5 billion years is pretty much the beginning of when we start to see really good passive margin sequences and things that are purely signs of tectonics, modern tectonics. There seems to be a transition zone, but it breaks down before 2.5 billion years. You start to see things in the rock record, geology structures that don't exist today. You see things that aren't part of the modern tectonic regime. And that's one of the biggest points. Well, was plate tectonics in operation the whole time or not? This is the craton.
Mhm.
Stable platform, North America now, but this wasn't always craton. Craton's gotten larger over time, as has the continent, and parts have broken off and sailed away. But this is mostly Mesozoic tertiary deposits, and this looked a lot like this until the Rockies formed. But we're going to leave that aside. We're going to look here. You come here. Okay, Gulf of Mexico for reference, Florida. We come up, and here you see the Illinois Basin, East Interior Basin. This is all Paleozoic mostly. And you see how this just looks. You don't even need to know anything about this. You just look at this and you see how these units are arranged on the map. Now, all Phanerozoic, just like the stuff to the left here. And we're not going to talk about the Appalachians because that's a very complex geologic history. We're going to scroll up, and now you get to my area, the Upper Peninsula. Here's Minnesota for you, and here's Ontario. And you get up here, and looks completely different. And then you get back to Phanerozoic deposits up in the Hudson Bay area, James Bay area, and you see these pink parts, which are granitoids, and then you see these green parts, which are kind of greenstones for the most part. And these are all greenstone belts. They have different names. They're all Precambrian. Most of them are Archean.
Mhm.
Well, pretty much all of them are. I think there's a couple that might not be. That might be a little hair younger. But this regime, yeah, it's been deformed. Yeah, there's faults, but this looks like nothing anywhere else. I mean, even if you go to, the Rockies and the Appalachians, it doesn't look like this.
Mhm.
And that's really bizarre because basically what we had is we have a assemblage of greenstone belts, which are basically mafic lavas with thin sediments on top, very thin, nothing like we even see in the or in the Proterozoic at all.
So, from all of this, Steve says that we know that something different was going on early Earth before about 2.5 billion years ago, something that wasn't plate tectonics. But what exactly it was is still up for interpretation, but we have some ideas. Essentially, there is a general sequence of tectonic regimes we think have evolved over time through Earth's history and will continue to evolve, and we'll talk about this in a second. The first tectonic regime that we think was occurring, very early on Earth, just after formation, was a magma ocean regime, which is just what it sounds like. Essentially, you have the mantle and then a magma ocean. at Earth's surface because Earth was so hot, and this magma ocean was not yet cooling and forming hard, solid, rigid crust like we have today just yet. And then in the late Hadean, nearing 4-ish billion years ago. We're not exactly sure on the timeline of this. These are very fuzzy numbers, especially the further we go back in Earth's history. But we think nearing the late Hadean, nearing 4 billion years ago, moving into the Archean, which went from around 4 to 2.5 billion years ago, we had heat pipe tectonics, essentially the type of tectonic regime we think is currently going on Io, the volcanic moon of Jupiter. And this is a scenario in which Steve says essentially there's crust and then a partial melt of the upper mantle, but no upper mantle lithosphere like we have today. So the green you can see in the later diagrams are representing the lithosphere, or at least the lithospheric mantle. The uppermost part of the mantle we said was part of the lithosphere, as is the crust. But in this heat pipe scenario, there is a crust, but no mantle lithosphere. And then we get into the regime, the tectonic regime, where things start to get really interesting. And this is called
drips and plumes. This is what the Archean in North America looks like, where you just have a simple ocean crust, or crust, we'll just say crust, and it's mafic. And then you get these felsic bodies intruding, these granitoids, which actually deform and push down this ocean floor. Because like I said, it has sediments on it, but they're very thin sediments. It's nothing like today. So whatever was sourcing that sediment was probably little tiny high areas on the ocean floor. But true continents, I don't know. Like, people have postulated supercontinents or continental bodies back into the deep Archean, but those all need to be taken with a grain of salt. But basically what'll happen is you get this mantle convection, and this would be a mantle-driven system. So that leads to things moving and colliding, and instead of subduction, what you get is this pull down. And this pull down, this drip, if you will, starts to pull that mafic rock back into the mantle. And then since you still have a hot mantle, which at the time is about 200 degrees Celsius hotter than it is now. So even if we did have plates subducting into the mantle, then they wouldn't have got very deep, because the mantle was a lot hotter. They would have been reincorporated relatively shallow.
So essentially, one really important distinction between this drip tectonic regime and the current plate tectonic regime that Steve emphasizes is that plate tectonics, again, is the lateral movement of lithospheric plates across, the surface of Earth due to the mantle convection and slab pull, whereas the drip tectonics was more of a vertical process of the dripping down of crust back into the mantle, kind of like subduction, but vertically instead of laterally. And the plumes of, kind of like hotspots today, like we have Hawaii, Yellowstone, essentially lying over hot parts of the mantle that drive plumes of, material to rise and cause volcanism at the surface. Just a much more vertical process than large-scale plate tectonics is today. And also seemingly driven a lot more strongly by mantle convection than obviously slab pull is today, because slab pull drives the lateral movement of plate tectonics through gravity. And this drip tectonic regime is thought to have continued on throughout the Archean eon, and then, we'll talk about the exact timing of the transition to modern style plate tectonics later, but it's thought that around 2.5 billion years ago is when full, modern style plate tectonics might have finally been the global norm. But this transition was very slow and not globally instantaneous. And we'll talk later about when we think the transition occurred and how Earth might have looked like in the drip to plate tectonic transition period, which was a long period. And then finally, we have the, final tectonic regime of Earth, which is just going to be a terminal stagnant lid, essentially no tectonic activity. And that will be, far future Earth when it has finally lost all its heat. So what did Earth look like during this pre-plate drip tectonic period in the Archean from around 2.5 to 4 billion years ago? And when did continental crust differentiate from oceanic crust? So again, going back to what we talked about in the first part of the video, there are two types of crust on Earth, the blue parts and the green parts. And essentially this is ocean and continental crust. And obviously, from this view, we could just say, oh, well, the ocean is blue because it's covered in water. But the crust underlying the ocean and the crust that makes up continental crust, that makes up land that we live on, these two crusts are very different in composition. And they underwent tectonic processes that caused them to differentiate, to become, either oceanic crust or continental crust. And their compositional differences lead to behavioral differences. There's a reason that ocean crust always subducts under continental crust. Oceanic crust forms at mid-ocean ridges and is mafic, and thus thinner and denser than continental crust. And so it subducts underneath continental crust, which is thicker and more buoyant than oceanic crust, and it forms at subduction zones and is felsic. Mafic and felsic are just terms relating to the composition of the crust. Mafic means it's relatively more silica poor, silicon and oxygen poor, whereas felsic contains a lot more silica or silicon and oxygen. Essentially, you don't really need to know what that means other than the fact that more felsic material is more buoyant, is less dense, and more mafic material is more dense. That's why oceanic crust can subduct and continental crust does not subduct. But if continental crust forms at subduction zones, does this mean that there were no continents before plate tectonics? Well, Steve says there is evidence for the formation of some early felsic crustal material around 3.8 billion years ago, long before plate tectonics was the global regime. Moreover, many studies suggest that much of the continental crust, potentially a majority of the continental crust that is around today, formed during the Archean, before 2.5 billion years ago, before plate tectonics was the global regime. So how is this the case if continental crust formation necessitates subduction? Well, remember that Steve said subduction does not mean plate tectonics. Subduction can occur in other tectonic regimes. It's just not exactly the same thing when we think about the way that plates subduct, which is a very lateral and rigid system. So essentially, it is possible that drip tectonics, or some sort of drip to plate transitional global tectonic regime, could have led to the formation of the first very early pods or small land masses of continental crust before plate tectonics was the global regime. I had previously shown this figure in that video that I mentioned that was, tectonic plates versus crust, explaining how early continental crust differentiated from oceanic crust during the Archean eon. However, as you see here, this is clearly a plate tectonic regime. And I now know, and probably the people that made this figure now know, that it was probably more likely a drip or drip plate transition tectonic regime than this rigid global plate tectonic type of system. And it's important to note when we're thinking about this that the reason subduction drives the formation of continental crust, and also the reason that we originally thought that it necessitated plate tectonics, is because subduction drives what we call partial melting, which is exactly what it sounds like, of magma, which leads to the formation of more felsic material, felsic continental crust. Why? Because if you take a bunch of rock that has both felsic and mafic material in it and you melt it, felsic material melts at lower temperatures than mafic material. Therefore, if you take a lithospheric plate that contains oceanic crust and you subduct it into the mantle and it begins to melt, the first thing that's going to melt out of that crust is the more felsic components. And because these materials melt out, they rise, they form melts, and hot material in the mantle rises through the lithosphere, rises, up to the crust, and it causes volcanism at these subduction boundaries. And this volcanism is releasing felsic material because that's the stuff that melted out. You're never going to get a melt that melts evenly and all at once and releases all the material to the surface. It's always going to start with the stuff that melts at the lowest temperature because that's what it reaches first. The temperature rises as it sinks through the mantle, and when it hits the very first temperature that is required for any of that material to melt, that material leaves the system, goes to the surface, and leads to the formation of felsic, at the time on early Earth, pods of continental crust. Not this big slab here. Obviously, this picture is of modern Earth, but you get the picture. And so that's why we originally thought that plate tectonics, specifically subduction zones, were required for the formation of early continental crust. However, again, like I mentioned earlier, we now know and think that it's possible that some subduction-like processes were occurring during the drip tectonic regime, as well as the drip to plate transition tectonic regime that we think could have driven the formation of the first continental pods, or pods of continental crust or land. So back to our original questions I asked, I don't know how many slides ago. What did Earth look like during the pre-plate drip tectonic period in the Archean, and when did continental crust differentiate from oceanic crust? Well, Steve says it was likely an ocean-dominated world with some maybe Hawaii-like islands here and there that popped up due to the more hotspot-like drip and plume tectonic-driven volcanism going on during this time. Again, think more vertical and like individual isolated spots rather than horizontal strings of mountain building and whatnot like we have today. And then as things shifted from drip to plate tectonics, more continental pods began to form. And then finally, as plate tectonics became the more globally continuous regime, these pods began to collide because subduction between them would, eventually allow them to meet and form larger land masses. And again, that happened over and over again until they could accrete into very large land masses that formed early cratons that we now have, underneath a lot of our continental land masses today. So when exactly did this transition from drip to plate tectonics fully occur? Well, Steve says that it was
probably about 3.2 to 2.5 billion was the transition. And then we got something resembling what we would recognize today. Now, obviously, there was still, over time, the lithosphere is getting thicker. It didn't just get thicker overnight at 2.5 billion and start driving plate tectonics.
So again, he emphasizes that this transition was not at all instantaneous. It marks a period of about 700 million years. So it happened very slowly and heterogeneously across the globe. It wasn't like one day it was drip and one day it was plate. It was probably drip-ish in some areas and plate-ish in some areas, but not continuous. And he even says that hotspot volcanism today, things like Hawaii, Yellowstone volcanism driven by hotspots in the mantle rather than large-scale plate tectonics, might be relics of this more drip-like tectonic regime. He even said that hotspots will likely go extinct in the coming year. I mean, not soon, but will probably cease to exist in Earth's future before plate tectonics comes to an end. And then eventually, again, like the diagram showed earlier, will come to a stagnant lid tectonic regime, essentially no tectonics once Earth has lost all its heat. So the take-home message from my conversation with Steve, which, by the way, was like 3 hours long, I had to cut it quite down because it was, we are geologists, we get to talking. But the take-home message is that not all tectonically active bodies have plate tectonics. This not only applies to early Earth, but also other planets and moons, like, for example, Europa, Io, Enceladus, and other moons of Saturn and Jupiter. Europa, for example, is a moon of Jupiter that has an ice-covered liquid water ocean, just like Enceladus, and we think that these moons, well, we don't think, we know they're tectonically active. I mean, look at the surface of Europa. We can see tectonic features, and we also see plumes literally jetting out of Enceladus' south pole constantly, so we know there's tectonic activity. Obviously, they are losing heat in some way. We also see on Io, the volcanic moon of Jupiter, the most volcanically active body in our solar system, the obvious loss of heat through volcanism going on. And so it is also tectonically active, but these moons don't have plate tectonics. Why is this an important distinction? Well, we have to be careful when interpreting their surface tectonic features because their tectonic regimes are different than our own modern plate tectonic regime. And typically our first go-to response to seeing any feature on another planet or moon is relating it to something we see on Earth, which is a good first go-by, but obviously cannot be made as a direct comparison. Likewise, since moons like Europa, Io, Enceladus, and other moons of Saturn and Jupiter are heated by tidal stretching, the gravitational pull and stretch driven by the huge gravity of Jupiter and Saturn, rather than driven by internal heat like Earth, this might heavily affect the way that heat is dissipated through their bodies and the way that obviously tectonics operates on these types of bodies. And also with that comes differences in composition and size and gravity and orbit and so many other things that are probably affecting their tectonic regimes and the way that tectonics operates on them. But overall, that is to say, it's important for us to understand the history of tectonics on Earth and what that might have looked like so that we can interpret these other worlds and kind of the stage of tectonics they might be in, as well as how it might progress in the future. So I hope you guys enjoyed learning about the difference between plate tectonics and tectonics today, as well as hearing from our fellow YouTube geologist, Steve Baumann. Thank you so much for being on again. And if you want to see more of his stuff, I swear he's got like hour-long amazing lectures where he draws like diagrams and stuff of the things I was trying to explain, but probably not properly. And so if you want to check out those, I will link a video up here. I'm sorry if you hear crinkling right now. It's because my cat is licking a plastic bag. It's just something she likes to do. I don't know. Don't worry, she doesn't eat it. Anyway, so check out Steve's video and I will see you guys in my next one. Bye.